Hello guys and welcome again. In this lecture we will see the image gradient operations, namely Sobel and Laplacian operations. So let's start. First I will create a Python file. I will call it image gradients.py. As usual I will import CV2 and numpy. I will read an image from data. So in this file here data I will have some images cv2.imread. I will give it a path, so data, and then I will read the briefs two images, and then I will read it as grayscale, so I will give it 0 here. Let's show this image cv2.imshow original and give it the image, and then cv2.imshow or cv2.waitKey 0. Let's show it first the original image. I will call Python image gradients.py, and here as you can see this is the original image. So if I convert it to grayscale image, so it looks like that. The first thing I want to do now is the Laplacian. So I will call the image Laplacian, and I will cv2.Laplacian. I will give it the image, and cv2.cv64f. So this is the output, this is called the d-depth, which will define how the output will be. So here it will be 64 floats. The OpenCV operations like the Laplacian and Sobel support just the 64 and 34 or 32 floats. So we need to convert this to uint8 to make the imshow operation or the other CV2 operations able to read this or to show this image. So for that I need to convert this by using Laplacian. I will use the same name, and I will use numpy.absolute this Laplacian as type np.uint8, and let's show this here cv2.imshow Laplacian, and then give it the image Laplacian, and let's show it here. So this is the Laplacian, and as you can see this is a binary image, and in that case many image processing operations like the edge detection can be done easily on this type of images, as we will see later. Now let's do another type of image gradient operations, namely the Sobel. So we have Sobel for the horizontal and Sobel for the vertical direction. So this will detect cv2.Sobel and we'll give it the image, the d-depth, here cv2.cv64f or 32, and this function will take the image and the d-depth on dx and dy. For the horizontal direction we need to give this as 1 and the y as 0. So I will give it here 1 and 0, and it will take the kernel size, so you can give any odd number. So kernel size, key size, and I will give it 3, and I can just copy this from here and put it here, and the thing that will change here, just will give this 0 and this 1 to get the Sobel in the vertical direction. We need to apply also this operation on these images to get them in the UINT format. So I will create here SobelX is np.absolute of this SobelX, and as type np.uint8, and just me copy this here and replace y by x by y. So here y. Let me show them here. So cv2.imshow, and this SobelX, we'll give it SobelX, and the same also for the y. So here we have SobelY and SobelY like that. Let me show them here. So this is SobelY and this SobelX, as you can see. We can combine this, the horizontal direction with the vertical direction like that, and getting the image like so. If I come here and say combine the image, and this will be cv2 weighted, add weighted, giving it the SobelX and 0.5 equal alpha and beta, and then SobelY and giving it also 0.5, and I will give gamma as 0, and let's show this image here. So cv2.imshow, I will call the window combined and call it here combined. Let's close this and run the image here. So this is these two operations combined, the SobelX and SobelY. This is the Laplacian. So when we combine these two images, we get this one. And as you can see, this is the original grayscale image, and this is a binary image which resulted from the SobelX and SobelY combined. We can apply this on another type of images or another image. So if I, for example, use an image here, bricks.jpg, and see how this operation working is. So this is very small image. As you can see, this is the original image. We can augment, of course, the brightness of this image, and that can help these algorithms detect these lines. If I apply this in another image, like Sudoku image, for example, and call here the Python, so this is the combined, this is SobelY, SobelX, the Laplacian here, and the original image. So we can see here SobelX and Y, and the resulted image of combination of SobelX and SobelY. Usually we are working on this combined image when we're doing some operations like edge detection, for example, or contour detection.